So we were talking about natural convection, and essentially we're going through the correlations for the Nusselt that are summarized in your textbook in table 8.2 for different geometries, right? So the same thing happened for forced convection, external and internal. We have tables that summarize those equations for the nozzle that we require for calculate the convective heat transfer coefficient that finally help us to get the heat transfer rate, right? And here I'm just showing the sphere geometry, or marking the sphere geometry, because it's one of the common geometries we typically deal in conduction and forced convection, right? The plates, the cylinders, and the spheres. But as you can see, you have several others like inclined cylinders or even cones. So you can find a bunch of different geometries in this natural convection table for nozzle correlations. And at this point, it is important to make some important remarks regarding natural and forced convection. And you should have in mind that in general, heat transfer coefficients in forced convection are typically much higher than those in natural convection. And sometimes the error involved in ignoring natural convection might be considerable, especially if you are working at very low velocities. So just as a recall that we have already discussed this, if we imagine that we have a flat plate, right, or a plate, the Nusselt number in forced convection is proportional to Reynolds to the 1/2, whereas in natural convection is proportional to the Grashof to the 1/4. Remember, in forced convection, it is the Reynolds that tell us which regime we are dealing with, right? And whereas in natural convection is the Grashof number, which becomes important, or it is the Reynolds for natural convection. Then the parameter Grashof over Reynolds square represents the importance of natural convection relative to forced convection. And this particular textbook has this plot, figure 827, that helps you to find the demarcation of different flow regimes on Reynolds versus the Grashof for different geometries. And it tells you when mixed convection becomes important, or forced convection, or natural convection. Okay, so you can consult this figure. However, if you don't have your textbook available, because you won't be carrying your heat transfer textbook with you all the time, one simple way to determine if natural is important, natural convection is important, is by getting the ratio of the Grashof versus the Reynolds square. So if the Grashof versus the Reynolds square is much, much, much less than 1, natural convection is negligible. If the Grashof over the Reynolds square is much, much, much bigger than 1, forced convection is negligible. And if the ratio Grashof over Reynolds square is equal to 1 or approximate to 1, like 0.8, 0.9, right? Forced and natural convection both are competitive. So you need to add to your evaluation of the process the natural element, the natural convection element. You cannot disregard natural convection, because both of them are comparable, both of them are important. And as I already mentioned, this typically happens when you are dealing with low velocities. So either you can use your table in your book or your graph in your book, but if you don't have available the book, for some reason, you can just simply do the Grashof over the Reynolds square and determine how important might be the natural convection, right? Again, natural convection is going to be important mainly in situations when you are dealing with low velocity phenomena. So natural convection can help or hurt the forced convection heat transfer depending on the relative directions of buoyancy induced and the forced convection motions. And I put here some examples for you, where in blue, due to the direction, right, the buoyancy induced and the forced convection motions, these natural convection is helping the forced convection. Where areas here, as you can see, we have different relative directions, right, in this plate. So in this case, natural convection is going to hurt the forced convection heat transfer, right? So again, the blue ones represent when natural convection is going to help heat transfer by forced convection, and the red one is going to hurt, and depends on the relative directions. So again, have in mind this figure, and this figure is just mentioning these equations because these equations were the ones that were used to build these lines, these trends, okay? So you have these equations A55, A56B, and A in your textbook, and these equations essentially were used to build these lines. But again, if you don't have your book available, just by knowing the relationship between the Reynolds and the Graf-Hof, you can determine if natural convection becomes important or not. So when natural convection should be included, then we need to calculate a Nusselt number for combined natural and forced convection. So we need to add the element of natural convection, right? So several review of a lot of experimental data suggests that the Nusselt number correlation for this case, when both natural and forced convection are important, is given by this equation, okay? Where NUF is the pure force Nusselt or pure force convection Nusselt, and NUN is the pure natural convection Nusselt, okay? And this N, this little N here on top, this is equal to 3 for vertical plates and 4 for spheres or cylinders in transverse flow. And you will use a plus sign here in this equation when the flows are in the same direction, when they are helping, right? And minus when they are in opposite directions, when the natural is hurting the forced heat transfer, right? Like we observed in the images in the previous slides. So this is an equation that you have in your book. Is in page 546, chapter 8 of the Crate, the 8th edition. So you have there the nomenclature, what is N, and the plus and minus, and this equation. So this equation is equation 8.57 in your textbook, the 8th edition. So let's solve a problem so you can see how to use this equation to mix both Nussels. So combined convection, we have a hot air balloon that measures 14 meters in diameter and is moving horizontally at a velocity of 1.2 meters per second relative to the wind at an altitude of 1,500 meters above the sea level. The temperature of the fabric, which reflects the average temperature of the air inside the balloon, must be 50 Celsius. So that could be the surface temperature, right? That is the same of the air inside the balloon. To maintain its altitude. Estimate the rate at which thermal energy must be supplied to the balloon by its propane burner system. So we need to know the heat transfer rate we need to supply by the propane burner system to maintain this balloon. So we know what we know. We know the free stream velocity, that is 1.2 meters per second. We know the diameter of the balloon, that is 14 meters. We know the T-wall or the surface temperature of the balloon being 50 Celsius. This you can take from tables. So this is the temperature of the surroundings or the ambient temperature at 1,500 meters above sea level. And this is from another textbook, but it seems your book also has this value. So it would be 5 Celsius, the temperature of the air at 1,500 meters above the sea level. We are going to get the T-film temperature, right? Because that's customary, or that's the strict way to solve problems in dealing with convection. So T film is T wall plus T surroundings divided by 2. So 50, the wall, plus 5, the air temperature at 1500 meters above sea divided by 2 is 27.5 Celsius. So we are going to read the properties of air at the film temperature of 27.5 Celsius. And again, if, for example, during homework, you have time to interpolate, but in the exam, you won't have time for the interpolating, right? You are running against time. So you can read at 30, 25, whatever is the nearest value you have available in your table. Just don't forget to make the note. I read properties at 25, or I read properties at 30, because that was available, okay? So I can know at what temperature you read your properties. So just don't forget the note, because some people might say, okay, I'm going to read at 25. Some people can say, I will read at 30. So I need to be sure that you are reading properly those tables. Density of the air at T film, CP of the air at T film, the viscosity, the wall temperature, right? This is the viscosity of air at T film at the wall temperature, because we need both. K, the thermal conductivity of air at T film, and the Prandtl at T film for air. And the gravitation acceleration, because remember, the gravitation acceleration becomes important in our Grashof number, right? That includes this G, or gravitational acceleration. Here I calculate the Prandtl, but you can read it straight from tables. You can do whatever. Best thing is just to read. Go ahead and read from the table. So I just calculate my Prandtl with the properties I read, just to double check. Volumetric expansion coefficient. Again, we need it because we needed to calculate the Grashof number. And since we are dealing with a gas that is air, we are going to assume that air is an ideal gas. So how we calculate the volumetric expansion coefficient for an ideal gas? 1 over the absolute temperature, right? So 1 plus 27.5 plus 273.15 Kelvin, that gives me this beta expansion coefficient, right? If it is a liquid that we are dealing with, we go to tables, right? The next step would be to get the Grashof number, because the Grashof number is so important for natural convection. And remember, here we are evaluating both natural and forced. And I'm starting with natural first. So the Grashof is given by this equation that we evaluate last class, right? Where the beta expansion coefficient is something that we have. We know the acceleration of the gravity. We know the difference of temperatures between the wall and the surroundings. We are dealing, or our balloon, we are evaluating our balloon to be in a spherical shape, right? So diameter to the cube, and the kinematic viscosity to the square. And after putting numbers in our Grashof equation, I get 1.488 10 to the 13. The Rayleigh is nothing more than the Grashof times the Prandtl, right? And in this case, the Rayleigh is 1.061 10 to the 13. Since the Rayleigh is much bigger, or bigger than 10 to the 9, we are dealing with turbulent regime for this natural convection. Remember that the Nusselt becomes dependent on the Grashof and the Prandtl, or the Rayleigh, like we discussed last class. Now it is time to get the Reynolds for the part of the forced convection. So if I calculate the Reynolds, I get 1.021 10 to the 6. That would be also turbulent flow. So I have the two numbers that are important for natural and forced conversion, the Grashof and the Reynolds. So now it is time to decide which Nusselt form or correlation I'm going to use to evaluate both the natural convection and the forced convection, right? But I need to recall that I'm calculating a combined Nusselt, right? Because I'm considering both force and natural are important. So I recall my equation for the combined nozzle, that is this one, and I'm going to use a plus sign because the flows are in the same direction. They are helping, right? And I'm going to use n equals 4 because I'm dealing with a sphere. Okay, so now we know we are using plus and we are using 4 here. Let's get the nozzles then. And I'm going to start with the nozzle for a sphere in external convection. So I go to my table for forced convection, right? And it's table 6.6, page 414. And I get that for this Reynolds, the nozzle correlation for a sphere in gas under external convection is given by this equation, right? My Reynolds falls in between the two Reynolds that are permitted for this equation, right? My Reynolds was 1.021 10 to the 6, and this equation for a sphere allows me to use it between 4 10 to the 5 and 5 10 to the 6. So my Reynolds falls in that. So I'm going to use this equation from table 6.6, forced convection, external forced convection. So I just put my Reynolds, is all I need for using this equation. As you can see, Reynolds here, and Reynolds here. So I just put the Reynolds in my nozzle correlation, and I get a Nusselt of 5762.62 for forced convection. I have the nozzle force. Now I need the nozzle natural, right, to add them in our combined nozzle equation. So we go and look for nozzle natural for a sphere. And in the back table, there's only nozzle for a sphere with Grashof less than 10 to the 5. So we need to add an equation that allows us to use for Grashof bigger than 10 to the 5. And this equation is this one. So if you want to add it to your table, please, for a sphere for Grashof less bigger than 10 to the 5. So this equation is not there for natural convection for a sphere, so please add it. As we already expected, our nozzle depends on the rally that we already calculate, right, in the previous slides. And so by inputting the rally and the branch, we get a nozzle of around 823. So we are ready to combine our nozzle numbers. So nozzle combined to the fourth equals nozzle force to the fourth, plus, because the flows are helping, right? You already checked that, plus the nozzle natural to the fourth. Finally, our nozzles, after removing the fourth here, is 5763.21. That was the complicated part of the problem. The rest becomes straightforward, right? We get the H out of the nozzle, like always. And finally, the heat transfer rate with an area for that sphere of pi d squared, right? So pi d squared times the H value that we get from our combined nozzle, multiplied by delta T, give us a heat transfer or heat we need to supply. We need to supply 2.8 10 to the 5 watts through the propane burner for the balloon to keep in place. So as you can see in this problem, I already required to use both natural and forced convection. However, when you are unsure if natural convection plays a role, you need to check either your graph in the textbook or do the ratio Reynolds-Grashof, right, to determine if it is necessary to include the natural convection effect or not. Okay, so this was an example already prepared for you to add both, but in some problems you need to decide if you really need to add the contribution of natural convection. And how you decide that? Well, either with the ratio of the Reynolds-Grashof, or either you go to your graph in your textbook and determine in which area of the graph you are, and if mixed convection is important or you need to evaluate as mixed convection or not. So let's start with another important topic that is heat transfer with phase change. What we are going to cover in this phase change heat transfer, we are going to cover boiling and condensation heat transfer, pool boiling, and forced convection boiling. And we need to recall some terms that I'm sure you already know, but it's important to bring them back when dealing with boiling and condensation heat transfer. And the first one is boiling. Boiling is when the temperature of a liquid at a specified pressure is raised to the saturation temperature, Tsat, at that pressure, right? Condensation. Condensation occurs when a vapor is cooled and changes its phase to a liquid. During condensation, the latent heat of vaporization must be released. The amount of the heat is the same as the absorbed during vaporization at the same fluid pressure. And here is an interesting research going on graphene layer that can quadruple the rate of condensation heat transfer in generating plants. And you can see by the difference in the pictures, right? This one has already covered a layer, thin layer of graphene. Both condensation and heat transfer are considered forms of convection. Why? Because they involve a fluid motion, such as the rise of bubbles to the top and the flow of condensate to the bottom. So they enter in a convection heat transfer. That's the main reason. We have a fluid and that fluid is moving, right? Bubbles or condensate. We need to recall some important concepts because we will see those concepts in our H or heat transfer coefficient equations for convection and boiling. Okay, so we will see all of these in all those equations. So different from other forms of convection, these two, condensation and boiling, depend on the latent heat of vaporization that in this book is given by HFG, that's the nomenclature of the fluid, and the surface tension, right, by D sigma at the liquid vapor interface. Another important term to recall, saturation temperature means boiling point. The saturation temperature is the temperature for a corresponding saturation pressure at which a liquid boils into its vapor phase. Another important term to recall from thermo is the enthalpy of vaporization or the delta H of vaporization. And in this one, the enthalpy of vaporization or delta H of vaporization is also known as the latent heat of vaporization or heat or of evaporation, and is the energy enthalpy that must be added to the substance, typically a liquid, to transform a quantity of this substance into a gas. Okay, so these are terms that we need to have in mind because they will be included in all our equations to evaluate now convection when dealing with condensation and boiling, okay? So again, heat of vaporization, saturation temperature, and the delta H of vaporization. Yep. So important term, the pool boiling. And this pool boiling occurs in a stagnant liquid. That's important to mention. The fluid is not forced to flow by a mover such as a pump. So any motion of the fluid is due to natural convection currents and the motion of the bubbles under the influence of buoyancy. Then the heat flux that is QW at the surface during boiling is given by Newton's cooling law, because again, these ones, boiling and condensation, are part of our convection study, right? So then the heat flux is H times T wall minus T saturation. And this T wall minus T saturation is defined as the excess temperature, delta TE. Delta TE is a new definition, a new term that we are including right now, and is the excess temperature, and is the difference of the surface minus the saturation temperature. So if you can see, the Newton's cooling law changed a little bit in order to get the flux at the boiling, at the pool boiling, right? So this equation, we are now in chapter 9 in your textbook. And if you are following me in your textbook, yeah, is chapter 9 starts in page 564. So now let's evaluate carefully the boiling curve. And you have this boiling curve in figure 9.1 in your textbook. So this is just a screenshot of that figure. And the boiling curve helps us to describe the pool boiling that we already said that is a stagnant fluid. We are not moving, right? But we have natural convection happening and the bubbles, the rising of the bubbles, right? So we are going to define, as you can see, we define this curve in different areas, right? That are demarcated by these numbers. 1, this is the 2, this is the third area, the fourth area, and the fifth area, okay? And here we have images of how these areas look like, okay? So the first area, the area number 1, is the one defined by natural convection. And it happens at excess temperature less than 5 Celsius, right? So as you can see in this curve, we have the excess temperature plotted versus the flux, right? So our first area occurs as an excess temperature less than 5 Celsius. Is this area, is the area of natural convection. And as you can see, this is an image that represents that area, the natural convection area. And here we have liquid near the surface that becomes superheated and rises to the free surface of the pool, of the free surface of the pool by natural convection currents. That's why it's named the natural convection area, okay? Because it is represented by natural convection currents. The next regime in the boiling curve is the regime number 2, right? And I'm going to go back here. So we are here in the regime number 2. So the nucleate boiling happens between an excess temperature of 5 and 30. And the nucleate boiling can be divided in 2 regions. The region 1, characterized by the formation of isolated vapor bubbles from preferential locations on the surface called nucleation sites. And the region 2, when the bubbles begin to coalesce in vapor columns and slugs that retard the liquid motion near their surface. This happens as you increase the delta excess, right? When you move from 5 to 30. So this is how it would look like those regions. The bubble region, right? Isolated vapor bubbles. And this is when they start to coalesce in vapor columns, right? Like they look like this, like they start forming these columns as you move the temperature excess from 5 to 30. Then we have the third zone of our boiling curve. That is the transition boiling. And the transition boiling occurs between temperature excess of 30 and 120 Celsius, And here you have an unstable film boiling, characterized by the rapid formation of vapor at the surface. It is not desirable to operate heat transfer equipment in this regime, okay? Unless at the upper limit or onset of the stable film boiling condition, or name it the Leidenfrost point. So it is named Leidenfrost point, just a quick note here, in honor of J.C. Leidenfrost, who observed in 1756 that liquid droplets on a very hot surface jump around and slowly boil away. And I'm sure that you have seen that when you have very hot surfaces, right? And you put a liquid, the bubbles like jump and then they just evaporate, right? And locate at a minimum heat flux point on the boiling curve. These points correspond to the upper limit of the transition regime and represents the onset of a stable film boiling condition. So you can find that in the number 3. And this minimum heat flux point, this one that I'm talking about on the boiling curve, that is the transition regime from the onset of a stable film to boiling condition, is here, right? Minimum heat flux. So we are here. Finally, we have the fourth area that it occurs at temperature excess bigger than 120 Celsius. And we have here in this area a stable layer of vapor or a vapor blanket that completely covers the surface. And in this case, in this area, thermal radiation begins to dominate the heat transfer from the surface if the surface exceeds 600 Kelvin. Then in this area, when you are in this area, you need to use heat transfer coefficients that involve both combined convection and radiation effects. So in this area, you need to add the contribution due to radiation. Okay? When you are in field boiling or the excess temperature is much bigger than 120 Celsius, that is when radiation begins to dominate the heat transfer. So you cannot just calculate H for convection, right? You need to add the radiation term. And we will go through radiation after heat exchangers. And this is how it looks like, right? Stable film boiling. So you have all of these in the plot, again in figure 567. You have all these images that shows more or less how they look like. And you have all the different demarcation of the areas of the pool boiling curve. So everything is there in that figure, and it is explained in 9.2 section in your textbook, pool boiling. So this is how it looks like in pictures, okay? So this is various boiling regimes during boiling of methanol on an horizontal 1 centimeter diameter steam heated copper tube. So this is how it looks like the nucleate boiling, the transition boiling, and the film boiling. Okay, so these were actual pictures taken of how the flow look like in those three regimes: the nucleate boiling, the transition, and the film boiling. So now we are going to focus on nucleate pool boiling heat transfer because it's what we need to study, right? So we will have, in this case, in nucleate boiling heat transfer, increased heat transfer rates are attained at the nucleate boiling as a result of the intense agitation of the fluid produced by the motion of the vapor bubbles. So the Reynolds should be modified, right? So that it relates to the turbulence and mixing of the motion of the boiling process. So now we name the Reynolds as the bubble Reynolds, okay? So when we are dealing with nucleate pool boiling, now we need to a little bit rearrange our Reynolds number, and now it's going to be Reynolds bubble. And that's why this has this little b here, right? So the Reynolds bubble is going to be dB times GB divided by nu L, where dB is the average bubble diameter, GB is the mass velocity of the bubbles per unit area, and nu L is the liquid viscosity. So again, when dealing with the nucleate boiling heat transfer, we need to do this little arrangement to our Reynolds number. Okay, then we will have a Nusselt bubble, right? So our Nusselt bubble is going to be HB, the convective heat transfer coefficient bubble, the dB that we defined previously, that is the average bubble diameter, and KL, the thermal conductivity of the liquid. Where HB is the nucleate boiling heat transfer coefficient, defined as the flux divided by the delta T excess. And we already defined the delta T excess, right? So all these equations, they start appearing in your textbook in page 573, the Reynolds bubble, the Nusselt, and the HB. So they are in your textbook, page 573, page 574, all these equations. So this delta Tx, we already defined it, right, is the excess temperature. Delta Tx or delta Te, yeah. Delta T excess can be delta Te or delta Tx. But in all the time when dealing with these boiling and condensation, that delta T is between the wall and the saturation. Okay, remember we are now evaluating different phenomena. So our delta T, our gradient of temperature, or our driving force now become delta Tx. So the question here is delta Tx and delta Te is the same? Yeah, it's excess temperature. So we are going to use for solving for pool boiling. We are going to use this equation. It's equation 9.2, and it's a correlation for nucleate boiling heat transfer for a wide range of fluids. Okay, um, so it's it's a very simple equation. The only thing is that we need to read a lot of properties in this case, as you can see, because we have here Cl, the specific heat of saturated liquid. Q, this Q is the heat flux. H effect, the latent heat of vaporization. G, the gravitation acceleration. Rho L, the density of the saturated liquid. Rho V, the density of the saturated vapor. Sigma, the surface tension of the liquid to vapor interface. The Prandtl L, the Prandtl number of the saturated liquid. Rho L, viscosity of the liquid. N equals to 1 for water and 1.7 for other fluids. CSF is an empirical constant that depends on the nature of the heating surface fluid combination and whose numerical value varies from system to system. And to get this empirical constant, you need to go to table 9.1 in page 576. So this I take straightforward from your textbook, and it helps us to calculate the heat transfer in nucleate boiling, okay, for a wide range of fluids. And as the author of your textbook notes here, this equation 9.2 requires that property values be known very accurately. In particular, note that sensitive of the Prandtl number effect on the heat flux. The most important variables affecting CSF of these empirical constants are the surface roughness of the heater, which determine the number of nucleation sites at a given temperature, and the angle of contact between the bubble and the heating surface, which is a measure of the wettability of a surface with a particular fluid. So as you can see, as the author is saying, the values of the properties should be known very accurately. Okay, so here that means that the most recommended thing to do is to interpolate if you don't have the exact value. Okay, if you want a very accurate final value of heat transfer.